All right, our next paper in this session, we have Pei-Lin Xu, and his paper is on equivariant contrastive learning for sequential recommendation. And get those slides up. All right, take it away.
Hey everyone, I'm Pei-Lin Zhou, a PhD student at DSA Information Hub, HKUST Guangzhou. Today I'm very happy to share our work, Equivariant Contrastive Learning for Sequential Recommendation. This is a joint work with Jingqi, Yueqi, Qichen, Yining, Jabon, Shoujin, and Song Kim. One key challenge of recommendation research is a data sparsity issue. This issue arises because the user-item interaction data, which is the foundation of sequential recommendation, is typically limited compared with a large number of users and items. For example, we have maybe millions of users or items. So the problem here is how to generate satisfactory recommendation with sparse interactions. One widely used approach is to employ the invariant contrastive learning paradigm. In this context, invariant means the representation acquired from the original instance and the one obtained from its corresponding augmented instance through contrastive learning, they are highly similar. Essentially, these invariant methods aim to make the sequence encoder insensitive to various data augmentation techniques. To accomplish this, data augmentation techniques are applied to the original sequence in order to generate positive whales. Whales originating from different sequences are treated as negatives. Subsequently, the contrastive loss is employed to bring positive whales closer together while pushing negative whales apart within the embedding space. For instance, one of the most notable invariant contrastive learning methods known as CL4S-REC, this method initially employs 3 types of sequence-level data augmentation strategies, including item masking, reordering, cropping to create positive whales. Subsequently, they utilize info-NCE loss to encourage user behavior representations to be invariant to all these augmentations. However, we observed that some sequence-level augmentation methods, such as item cropping, may break critical associations among items in the original sequence. As a result, the actual relationship of the positive instances may not be semantically identical. For instance, consider a user's behavioral sequence like smartphone, headset, lipstick, blouse, socks, sneakers. The 2 generated positive whales, namely smartphone, headset, lipstick, and lipstick, blouse, socks, sneakers. These 2 sequences do not share identical semantics. The former primarily emphasize on digital products, while the latter predominantly focuses on clothing. Consequently, we classify these sequence-level augmentations as invasive augmentations. It is evident that learning invariant representations for invasive augmentations may not be optimal. In contrast, the impact of augmentations at the feature level on semantics is easier to control compared to that of sequence-level augmentations. Thus, feature-level augmentations such as dropout are considered to be mild. Learning invariant representations with these mild augmentation strategies seems to be more appropriate compared with invasive ones. So to verify our observations, we compare the performance of invariant contrastive learning with different invasive augmentations and mild augmentations. As shown in this bar chart, mild augmentations, which denoted by yellow bars, always have performance improvement on the base model. The base model is dashed line in the figure. And in contrast, learning invariant representation for invasive augmentations, these green bars, their performance is less desirable. It doesn't consistently improve the performance and sometimes even worsens it. This empirical study indicates that the current invariant contrastive learning paradigm is more suitable for mild augmentations conducted at the feature level. Then a natural question arises. How can we build a more reliable contrastive learning framework that benefits from both mild feature-level augmentations and invasive sequence-level augmentations to further improve the performance of sequential recommendation? So to bridge this gap, we propose a new framework. It's called Equivariant Contrastive Learning for Sequential Recommendation. We designed this framework to utilize these two kinds of augmentations together. The core idea behind is to leverage mild and invasive augmentations within a unified framework to encourage both the invariance property and the equivariance property of contrastive learning. On the one hand, invariance for mild augmentations is capped. Invariance makes representations insensitive to non-essential variation. This is achieved through invariant contrastive learning. On the other hand, our method can learn equivariance for invasive augmentation. Equivariance encourages representations to change predictably according to augmentations. This is achieved by designing an additional task to predict the augmentation operation applied to the input. So our proposed framework includes three main components: a user behavior encoder, a generator, and a conditional discriminator. The main goal of the user behavior encoder is to capture key patterns from user interactions and recommend the most appropriate item to the user. Here, we introduce invariant contrastive learning for the user behavior encoder to learn invariant features for mild augmentations. Generator and the conditional discriminator are used together to encourage the user behavior encoder to learn equivariance for invasive augmentation. So, how to learn invariance for mild augmentations? In our work, we use feature-level dropout masking to generate positive instances. Other samples in the batch are regarded as negative samples. Then, we adopt info NCE loss to pull the positive examples closer and push negative examples away in the semantic space. And to learn equivariance for invasive augmentation, we firstly randomly mask several atoms of the original sequence. Then we use generator to recover randomly masked atoms to obtain the partially substituted user interaction sequence. Finally, we use conditional discriminator to perform the replaced atom detection task regarding the output representations of the user behavior encoder as conditions. With this method, we construct fake interaction sequences with smaller semantic perturbations, which poses a challenge for the discriminator to correctly identify the substituted items. In the training stage, item embeddings are shared across all three modules. The parameters of the user behavior encoder and discriminator are also shared to avoid overfitting. All components of this framework are trained in an end-to-end manner. Therefore, the whole framework is optimized with the combined loss function. In the inference stage, we remove both the generator and the conditional discriminator and only use the user behavior encoder to accomplish the next item prediction task. The experiments are conducted on 4 real-world and widely used datasets. Following the same pre-processing steps used in previous papers, we remove all atoms and users that occur less than 5 times in these datasets, and we evaluate model performance in a full ranking manner for a fair comparison. For the overall performance, we can clearly see that our framework consistently outperforms both state-of-the-art basic sequential recommendation models and contrastive learning-based sequential recommendation models on all data sets in all evaluation metrics. This consistent improvement demonstrates that our proposed solution effectively helps make next item prediction on both sparse and dense data sets. Actually, there exist several options for mild augmentation and invasive augmentation, leading to different combinations of augmentation strategies. So, it is necessary to investigate their impacts on the performance of our framework. For mild augmentation methods, we experiment with dropout, feature normalization, and feature perturbation as mild augmentations. For a fair comparison, we fix the invasive augmentation, namely mask item substitution, and we use grid search to obtain the best performance of our framework with respect to these three different mild augmentations on movie length 1 million dataset and Yelp dataset. The results are shown in this table. We can observe that dropout achieves better performance than both normalization and perturbation. And to investigate the impact of invasive augmentations, we test mask item substitution, random item substitution, insertion, deletion, crop, and reorder. For a fair comparison, we fixed the mild augmentation method to be dropout and search the optimal hyperparameters for every invasive augmentation. We can see that mask item substitution significantly outperforms the other 5 invasive augmentation methods in most cases. In particular, masked item substitution brings more performance gain compared with random atom substitution. A potential reason may be that masked atom substitution can better preserve important correlations among atoms in the original user sequence, thus empowering the conditional discriminator to capture small differences. In our ablation study, we can see that both contrastive loss and replaced atom detection loss contribute to performance improvement. This observation verifies that both invariance and equivariance are important properties for enhancing the quality of item representation, and our method could exploit the complementary nature between them. In the hyperparameter study, we examined the impact of 5 critical hyperparameters in our framework, including batch size, the temperature, window size, mask ratio, and dropout ratio. We adjust one hyperparameter at a time and keep the others optimal to control our variables. You can check the discussions about these hyperparameters in our original paper. So to conclude, in this paper, we propose the equivariant contrastive learning for sequential recommendation. This framework can effectively utilize both mild and invasive augmentation to enhance user behavior representations. To achieve this, we propose a conditional discriminator to capture user behavior discrepancies between original interaction sequences and their edit version, which enables learning equivariance for invasive augmentations. Finally, we conduct various experiments to show the effectiveness of our methods over both classical and state-of-the-art contrastive learning-based sequential recommendation models. Thank you for your listening. If you have any questions on our paper or codes, please feel free to contact us. Thank you.
All right, we have some time for questions. Come up to the microphone. I think we have a question here.
Thank you for your amazing presentation. Can you back your motivation experiment?
Back to the experiment.
Is your motivation
Okay.
experiment?
You mean
next? Yeah,
this page, right?
Yeah, we can observe the yellow augmentation methods focus on embedding augmentation, and the another they focus on, sequential structure. You change the sequence, so you get augmentation. Do you think we can observe that embedding augmentation always show better performance than structure augmentation? So do you think we need more attention in embedding augmentation rather than structure augmentation?
Yeah, that's a very good question. So here we this empirical study show that the invariant contrastive learning is appropriate for can benefit from the meld augmentation. So you can see from this chart, the meld augmentations always improves performance, but invasive augmentation sometimes even worsens it. But the question here is we want to get benefits from both meld augmentations and invasive augmentation. We don't want to ignore the invasive augmentations because we think we can find better ways to exploit the invasive augmentations. That's the motivation why we propose different ways with existing methods that we instead of just trying to encourage the model to be invariant to the invasive augmentations, I mean sequence level augmentations, we try to encourage the model to predict the augmentations applied on the sequences. So by doing so, we achieve better performance than only using invariant contrastive learning. So that's our motivations. I hope this answers your question. Thank you.
Yeah, thank you.
Other questions? So could you go to the slide with the hyperparameter part?
Hyperparameter study?
Yeah. Yeah.
Okay.
Jumping around here.
Maybe this page. Oh, sorry. This
Yeah,
page,
yeah.
hyperparameters.
So one of the things you say in the paper is that one of the challenges with batch size is that you find negative examples that are actually they're false negatives, basically. You assume all of the examples in the batch are negative except for the one that you have. So I'm wondering, might there be value in actually trying to look at the similarity between the sample and the actual item to try and predict whether it's a false positive, or I mean a false negative, and not use it, basically be more discriminating about the contrastive examples.
Yeah, we don't show these negative samples here. So can you repeat your question, please?
So the question is basically, you're sampling, you're assuming all of the other items, in the batch are negative, but you could actually try and figure out if they're negative, if they're too close to the thing that you're trying to predict.
In our paper, we just treat in a single batch, the other samples in a single batch are regarded as negative samples. We didn't use any strategies to...
Right. So anyway, I was just wondering if that was something worth trying. Yeah.
Maybe we can explore this in our future study. That's a good suggestion. Thank you.
All right, let me just check online. There's a question about the difference between invariance and equivariance.
Okay, that's a very good question. Yeah. I think people may be confused about these two concepts. Actually, these two concepts are mathematical concepts. And briefly speaking, equivariance studies how transformations of the input user behavior sequence are encoded by the representations. And invariance is a special case where a transformation has no effect. Here is the comparison between these two concepts. So from the mathematical perspective, the concept of equivariance can be defined as its formula, where G belongs to the group of invasive data augmentation methods, and TGSU denotes the function with which G augments an input-user interaction sequence SU. F theta is the user behavior encoder that encodes dynamic user interest into behavior representations. And TG dot denotes a fixed transformation. So it's worth noting that the invariance learning is essentially a special case of equivariant contrastive learning when the identity function is used for TG dot. So that's, I hope this can explain your answer, your question. Thank you.
That's great, thank you. I think that's probably all the time we have for questions, so let's thank the speaker again.
Thank you very much.